Hey everybody, it's Tuesday, May 4th. As you can see here in the aim today, our goal for today's video is to review the free response question that was posted yesterday. Now, between the video reviewing the multiple choice homework and the video that was going over the free response question you were assigned on Friday, I figured just this short 13-minute question was enough work for yesterday. And so let's get into it. This problem here said a wooden wheel of mass m consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal, shown above. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. Now, this rolls without slipping issue is something we've talked a lot about this year, that yes, there needs to be friction exerted on the thing so that it rolls without slipping, but it's not enough friction usually to take the energy away from the system. Now, here, the fact that they said it was the force of static friction was generous, I thought. It should be pretty clear to everybody that it's not kinetic friction because the wheel isn't actually sliding. Nevertheless, I thought it was pretty good that they said it was a force of static friction, so they make it totally obvious to you what's going on. Now, the first part of this question, or at least the first part of part A of this question, said on the diagram below, draw and label the forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. Then it says the lengths of the arrows need not indicate the relative magnitudes of the forces. So let's start with a super easy one. The force of gravity is going to start at the center of mass of the wheel, which is located at its geometric center, and it is going to come straight down. Since it does not say how long the things need to be or that the length should not indicate how big the forces are relative to each other, I'm just going to draw it long enough that I can clear, the ramp and the wheel and just give myself enough space to label it because they've asked me to draw and label the forces. So that's the force of gravity. It acts at the center of mass. And what you should have realized is the force of gravity is the only force that acts at the center of mass. The only other forces that are acting on this wheel are the normal force and the frictional force. And both of those forces are what we refer to as contact forces, meaning they act at the point of contact. And so that point of contact here is this point on the surface where the wheel is touching the ramp. So the only thing you should really know about the normal force is that it is perpendicular to the surface. And so it is going to act up somewhere in this general direction. And again, I'm just going to clear the wheel so I can put my arrowhead and then label it with its appropriate label. That's the normal force. So I'm going to write F with the subscript N. And the last force here, the force of friction, is also a contact force. It acts at the point of contact, and it is going to have to be drawn here and parallel to the ramp, unlike the normal force, which is going to be perpendicular. And so I'm going to try my best to do this with this digital pen as good as possible. And it's a little slanted, but it's going to look a little something like that. Not perfect, but good enough. And I'll label it here F with the subscripts F and S for the force of static friction. Now, hopefully you should have had that static friction force drawn there a little better since you were doing this on paper. Of course, you could use a ruler to do this as well, especially if you have trouble drawing straight lines like I obviously do. But take a second to pause this video here and check out this free body diagram. And when you hit play, we'll take a look at the scoring guide. Okay, moving on to the scoring guide here for part A1. This part was worth 2 points. So the first point says for a labeled arrow representing the gravitational force, starting at the wheel center and directed downward. The second point is for labeled arrows representing the friction and normal forces. Now, this next part is confusing, but I think you'll get it. It says, or a single arrow representing the resultant of the friction and normal forces, the force exerted on the wheel by the surface. Now, because the friction force acts parallel to the surface and the normal force acts perpendicular to the surface, some people like to think of these two forces as being the perpendicular components of a single surface force, if you will, which is going to act at some diagonal like this, or like the net surface force. I never taught you that because I think that's a totally weird way to think about it. And you don't need to do it like that. It's actually somewhat unorthodox to do that. So really, you could have had, that diagonal force or the normal force and the friction force as shown in this diagram above, and both of those would be perfectly fine. Now, they give some notes about what the friction and normal force should look like. It says the friction force should start at the wheel ramp contact and be directed up and left along the ramp. So like this. And it says the normal force should start at the wheel ramp contact and be perpendicular to the ramp and toward the wheel center. It does not have to go exactly through the center, but it must come reasonably close. Now, let's be clear. Since the normal force is perpendicular to the surface, if we are drawing it at the point of contact, it actually technically does go right through the wheel's center of mass. They said this is not an art contest, so they're not expecting you necessarily to show that, but it should be in the general direction toward the wheel center and come reasonably close to it. And so that means the diagram should look exactly as it's pictured up here at the top. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to part A2. All right, moving on. The next part here says, as the wheel rolls down the ramp, which force causes a change in the angular velocity of the wheel with respect to its center of mass? Briefly explain your reasoning. Now, I like this question because it really forces you to pay attention to what's going on. The fact that they're asking you here, which force causes a change in the angular velocity, I hope everybody realized, was basically their way of asking which force causes a torque. If you didn't realize that, well, then the idea goes like this. If the angular velocity is changing, then what that technically tells you is this thing is experiencing an angular acceleration, which should be clear because as it rolls down the ramp, it's going to get faster and faster and faster because it's accelerating. But because the torque is equal to I alpha, the rotational inertia, times the angular acceleration, the only possible way that it can experience a change in angular velocity and thus an angular acceleration is if there's a torque. Now, of course, there's a little more to it than just that, because the torque equation says the torque is equal to RF sine theta. So in order for a torque to be produced, there has to be a force. The force has to be some distance away from the pivot point, and the force has to be perpendicular to the position vector, or this vector R, which is drawn from the pivot point to the point of application of the force. And so really, as always, if they ask you to draw a free body diagram, they want you to go back to the free body diagram. So let's take a look here. The first thing that I hope was obvious to everybody is that the force of gravity here is not exerting a torque. The reason why the force of gravity is not exerting a torque is pretty clear. It's because it acts exactly at the pivot point here. So if we're talking about the equation RF sine theta, the reason why the force of gravity doesn't exert a torque is because the R is equal to 0 meters. It acts exactly at the pivot point. So that's force of gravity. Now moving on to the other forces, let's go with the normal force. The R vector in the torque equation is a vector that is drawn from the pivot point to the point of the application of the force. So for the normal force and the frictional force, because they both are contact forces which act at the surface, the position vector R is going to look a little something like this. And I'm just coloring this in here to make it easy to see. So hopefully you realize already what's happening. Notice that position vector is parallel to the normal force. That means in the torque equation, the angle is going to be equal to 0. And because the torque equation is RF sine theta, the sine of 0 degrees is 0, which is going to make the torque equal 0. The normal force does not produce a torque. And with that in mind, that exact argument for why the normal force does not produce a torque, I hope everybody realizes why the frictional force does exert a torque, because the frictional force is acting some distance away from the pivot point, and it's actually perpendicular to the position vector. And since the sine of 90 degrees is 1, that means the frictional force satisfies all of the criteria for a force producing a torque. So the answer to this part is a frictional force. If the wheel is experiencing a change in its angular velocity, that means it's experiencing an angular acceleration, which means it's experiencing a torque, because only torques can cause an angular acceleration. In order for a force to cause a torque, the force must act at some distance away from the pivot point and act with a component perpendicular to the position vector. a line drawn from the pivot point to the point of the application of the force. The only force that produces a torque, and thus causes a change in the angular velocity, is the force of friction. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on to the scoring guide. All right, moving on to the scoring guide here. The scoring guide gives you only 1 point for this part, and it says the correct answer is the friction force, and no points are earned if the wrong force is given. And what they give you the point for is for correctly explaining that friction is the only force that exerts a torque with respect to the wheel's center of mass. So it says this point is also earned for a, quote, causal chain of reasoning about forces, or in other words, that the gravitational force leads to a normal force and acceleration down the ramp, which leads to a frictional force, which exerts a torque or changes the angular velocity. But the key detail here is that the reason why the friction force causes a change in the angular velocity is because it exerts a torque. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to part B. All right, moving on to part B, the best part of this question, in my opinion, it says, for this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction on the wheel, exerted on the wheel, is 40% of the magnitude of the force or force component directed opposite the force of friction. That's so important, I'm going to say it again. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. Question says to derive an expression for the linear acceleration of the wheel center of mass in terms of m, theta, and physical constants as appropriate. So as you saw here, we had a force of gravity coming down, we had a normal force coming up, and we had a force of static friction acting parallel to the ramp, which I have drawn all sorts of wonky over here. And we have to consider the linear acceleration of the wheel down the ramp. I said it once and I'll say it again. It's really important for everybody to realize if in the beginning parts of a problem they ask you to draw a free body diagram and then they ask you to derive anything, it's supposed to be done using the free body diagram. If this thing is accelerating down the ramp, then we have to use the basic free body diagram approach for deriving acceleration expressions. Now notice, there are no actual full forces acting in the direction of the acceleration, but the component of the weight that's parallel to the ramp, or in other words, FGX, is acting down the ramp and opposite of the force of static friction. So if you remember, when we derived free body diagram equations, we always said we take MA and set it equal to the sum of the forces. Or in other words, we take MA and we set it equal to the forces going in the direction of the acceleration minus the forces going opposite of the direction of the acceleration. So we take MA and we set it equal to the force going in the direction of the acceleration, which is FGX, and we subtract the force going in the opposite direction, the force of static friction. Now, if you're looking at this and wondering, do I need to write MA equals the sum of the forces? I think it is a really smart idea whenever you are doing a derivation for you to start with a main principle of physics, or in other words, something that is from the reference table. If you're applying free body diagram techniques, just write the sum of the forces equals MA. If you're using conservation of energy, just write E initial equals E final. Make it super clear to the person who is grading your work that you know what you're doing. That's the idea. Now, of course, we've got to really make sure that we're being as specific as possible when it comes to this equation. I think the first thing I want to do, though, is just go back to this really important thing that I underlined here in the text of the problem. They tell us here the magnitude of the force of static friction is 40% the magnitude of the force component directed opposite of the force of friction. The force component directed opposite the force of friction is FGX. 40% of that is 0.4 times FGX. So what they're telling us is that the force of static friction is 0.4 FGX. So now we're pretty much ready to finish this thing up just with that one move. So we have MA equals FGX minus 0.4 FGX. And now I hope you see where this is going. Now we have two like terms. One FGX minus 0.4 FGX. And 1 FGX minus 0.4 FGX is 0.6 FGX. Now all we have to do, since the problem specifically told us to do this in terms of m, theta, and other physical constants, is sub in our equation for FGX. I hope you remember FGX is going to be equal to mg sine theta. Remember, it's not a cosine because sine and cosine switch on an inclined plane. So we have ma equals 0.6 mg sine theta. And notice, which is the real dirty trick in this problem, is that the masses cancel. Now, if you go back and look at the description, you might say that's weird because they told us to derive it in terms of m. And now there's no m because the m canceled. They always tell you variables that one might think are important in the equation, even if it's gonna cancel. The reason why they do that is because they don't want to give it away to you that it is canceling. And so even if they list a variable, don't be shocked or worried or whatever if it ends up canceling, because if it ends up canceling, it just means it doesn't matter. They didn't want to give it away to you that it was canceling by not listing the mass. That means here, the equation for our acceleration of this thing as it moves down the ramp is just 0.6 g sine theta. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own derivation. And when you hit play, take a look at the scoring guide. All right, looking at the scoring guide here, so the scoring guide says 1 point for an expression of the sum of the force components parallel to the ramp that recognizes that there are two forces with components parallel to the ramp. And then it says here, the expression need not be correct or consistent with the force diagram in part A. So even if you got this wrong, it seemed like if you just realized there are two forces that are acting parallel to the ramp, they would have given you the point for that. And then they give you 1 point for indicating that the frictional force is 0.4 FGX implicitly or explicitly, and correctly solving for the acceleration in terms of the correct variables. So notice here they have the sum of the forces parallel equals mg sine theta minus 0.4 mg sine theta. Then they write 0.6 mg sine theta over m, and then notice they canceled out the m's. Now, I guess if the big question is, if you wrote this and didn't cancel out the m's because it said in terms of the mass, would they give it to you? I think so, because it is correct. Now, of course, you want to simplify things when they obviously simplify. And so the masses cancel there. So you should cancel them. But in my view, did you have to get the full credit? I don't think so. Take a second to pause this video here and go over the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on to part C. All right, moving on to part C. Part C says, in a second experiment on the same ramp, a block of ice, also with a mass m, is released from rest at the same instant the wheel is released from rest, from the same height. The block slides down the ramp with negligible friction. Which object, if either, reaches the bottom of the ramp with the greatest speed? The wheel, the block, or neither? Both reach the bottom with the same speed. Now, based on everything we said about energy, you should know the answer to this question here. It's gonna be the block. But what I like about this part of this question too is that they ask you to explain it in terms of forces, which I think is really weird. And it's important to realize if you're explaining something about speed in terms of forces, there's really only one logical way that you can do that, and that's by using Newton's second law. Take a look at my answer. I wrote here, the block reaches the bottom with the largest speed. Make the conclusion known. Make the person who is grading your paper realize you know what you're talking about. All right, since we already said the wheel has a force of friction acting up the ramp, as well as a component of its weight acting down the ramp, the net force acting on the wheel is the difference between the component of the wheel's weight parallel to the ramp and the friction force acting up the ramp. On the other hand, the block of ice moves with negligible friction. So the net force acting down the ramp is the component of its weight parallel to the ramp only. What does that mean? This means the net force acting on the block of ice is larger than the net force on the wheel. Since the net force is directly proportional to the acceleration, and the block of ice and wheel have the same mass, the acceleration of the block of ice will be larger. And then the conclusion, since the block of ice has a larger acceleration, and that acceleration acts over the same distance for the wheel, the acceleration of the block of ice being larger will result in a final speed of the block of ice that is larger. Take a second to pause this video here and take a second look at this explanation. Add any parts of it that may be missing from your own. And when you hit play, we'll take a look at the scoring guide. All right, taking a look at the scoring guide here, this part was only worth 1 point. Notice here, it just said briefly explain your answer in terms of forces. So you didn't quite need to say all that. But notice the scoring guide here is super, super vague. It just says for a correct explanation in terms of forces. Their example is the wheel experiences a counteracting frictional force. So the block has a greater net force exerted on it and therefore has a greater acceleration. Now notice the key theme here is all about the size of the net force. There was a question sort of like this for inclined planes that we've answered already. If you remember, it was involving a block that was thrown up a ramp, slowed down to a stop, and then came down, and they wanted to know which one took more time. The argument for these kinds of questions are always going to be about the size of the net force. Now, of course, you can determine the size of the net force because we already drew a free body diagram. That's a key thing to recognize about this problem. Take a second to pause this video here and take a good look at the scoring guide, making sure you understand all aspects of it. When you hit play, we'll move on to the final part. All right, now the last part of the question here, part C2, says, now briefly explain your answer in terms of energy. So notice you didn't need to check the thing again. The block is still going to be faster. But now they just want us to explain it in terms of energy. This, I would hope by now, is in everybody's wheelhouse because we talked so much about this when we were going through rotational energy. What I wrote here is the block reaches the bottom with the largest speed. Just state my conclusion up front, letting the person who's grading my paper know what I'm talking about. It says the block reaches the bottom with the largest speed. Since both blocks start at the top of the same ramp, the same height, and have the same mass, they both start with the same amount of gravitational potential energy. Since the wheel has a force that causes a torque on it, which causes it to roll, some of the initial gravitational potential energy must be converted to rotational kinetic energy for the wheel to allow it to roll. Since the block of ice doesn't rotate, all of its initial gravitational potential energy will be used to cause the block to translate down the ramp, thus giving it a translational kinetic energy at the bottom equal to its initial gravitational potential energy. Then here's the payoff. Since the wheel's rotation requires some of its initial gravitational potential energy to be used to allow the wheel to rotate, rotational kinetic energy, the wheel will reach the bottom of the ramp with a smaller translational kinetic energy than the block of ice. Since the wheel reaches the bottom with less translational kinetic energy, it will move with a smaller speed at the bottom of the ramp. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. When you hit play, we'll look at the scoring guide. All right, looking at the scoring guide here, same thing. It was a 1-point question only. And it says for a correct explanation in terms of energy conservation. Very vague again. Their example was both object Earth systems lose the same amount of potential energy and therefore gain the same amount of kinetic energy. That is a fact. That is usually a thing that is confusing to people too. They do gain the same amount of kinetic energy. The difference is the distribution in terms of translational and rotational kinetic energy. Then says with the ice block, but not with the wheel, all the kinetic energy is translational and none is rotational. So the block is faster. And that's it. If you want to take another closer look at this part of the scoring guide, go ahead and pause this video here. But with that, that is it for this question. Make sure you use this information about the scoring guide to go ahead and score your response in AP Classroom. With that, that's it for today. Have a good one, everybody.